Hello everyone, welcome to the 12th week of discussion of the course Strength of Material course offered by NPTEL. The course instructor of this course is Professor Siman Kumar Bhattacharya. He is a professor from IIT Kharagpur. Myself, Asif Raza, I am TA of this course. I am a PhD scholar from Department of Civil Engineering, IC Bangalore. So, this session would be the last session in this discussion sessions, and nevertheless, you guys can post your doubts using the discussion forum. You can post your doubts, and I'll try to resolve your doubts as much as possible. Okay, so let's do this. Okay. So 12th week was all about springs. So I'll just give a simple thing. First of all, springs are used for what? To absorb an energy and to like restore the configuration or something like that. Yeah, just a simple thing. So the parameters involved in that. So first thing first, springs are like this. Okay, so suppose uh, you can say capital D is this, and this is the pitch. Uh, mm, this is the D, and if it is in natural configuration, that is termed as L0. Okay, I'll just write. So for a spring, uh, there is a spring constant or stiffness related to it. So it stores energy in terms of it will get compressed or stretch, and it will store it as half kx square, where x, where u is potential energy, k is stiffness of the spring, and x is extension. Okay, now deflection associated with this spring, or rather I'll just to calculate the stiffness of the spring. Suppose P is the force applied and delta is the deflection. It's calculated by taking GD4 by 64 R cube, and I'll just write it as R cube, and okay, where G is my modulus of elasticity, D is diameter of the wire through which the spring has been made. R equal to twice D, and that is radius of the spring. Sorry, not by d by t, the radius of the spring which has been spring or coil. Okay, and n is number of turns. Okay. Okay. Two more things. Uh, when springs are in series, that imply like it is denoted by this. First, this is K1, K2, K3. I can draw a K equivalent, and this would be equal, K equivalent would be equal to yeah. And one more thing, when springs are in parallel, K1, K2, K3, can draw one spring which would have the similar property. This K equivalent would be equal to K1 plus K2 plus K3. Springs act like capacitors, like in connections, I mean to say. Yeah, so this is what I wanted to say something. Yeah. Okay, so let's start solving questions. So I'll just jump. I'll start with a simple question first. Yeah. So this is okay. This we'll start from this. The question is, if the Y diameter of a closed coil spring is increased from 3 mm to 6 mm, other parameters remaining same, then deflection will decrease by a factor of. So first thing first, we should write what has been given. Wire diameter, that is D. If I say D1 was 3 mm and it changed to D2 as 6 mm, while the other parameters are same. We know the deflection formula is, as said earlier, H64 R cube N. Okay, so we'll use this formula. In the question, only D changes while other things would be the same. So we can write delta 1 is GD1464 R cube N, delta 2 to GD2 to the power 464 R cube N. Thus we can take delta 2 by delta 1 as D2 by D1 to the power 4. This is equal to 6 by 2 to the power 4, 2 to the power 4, that will be 2 to the power 4, that will be 16. and this is what is asking. If the wire diameter of a closed well, then will decrease by a factor of, so actually it will increase, right? Deflection GD4 64 R cube, and question needs a modification. Increase. Okay, so correct answer would be 16. Moving on to the next question. This is a very good question. Question is, a weighing machine consists of a 2 kg pan resting on a spring. In this condition, with the pan resting on the spring, the length of the spring is 200 mm. A weighing machine consists of a 2 kg pan resting on a spring. In this condition, with the pan resting on the spring, the length of the spring is 200 mm. When a mass of 20 kg is placed on the pan, the length of the spring becomes 100 mm. For the spring, the undeformed length and spring constant K are. So the question is, then in a similar way, I'll just I'm not drawing the weighing machine though, but in a way I'll just try to say, okay, let me draw that. Suppose this is the weighing machine of 2 kg. Now the spring is compressed and the length of the spring is 200 mm. When the additional weight, this is a 2 kg pan, then the weight, suppose 20 kg weight is applied on it, spring compresses more, and now the length becomes 100 mm. Okay, so we need to find what will be my undeformed length L0 and spring constant K. So we'll draw case by case. So we can say for sure that this 2 kg weight is balanced by the reaction force produced by the spring, and that would be Kx, where x is the change in length of the spring, and so let's draw this. So 2 times g, I'll just say mg is equal to kx, right? This is what I'm trying to solve. So 20 times, I'll just use the value g, not giving value is 9.81, k as this. This would be, since it would be a compression, so L0 minus 200. Okay, L0 minus 200. So as in this, I'm trying to use K as Newton per mm. Okay, so that it balance out on both sides. Okay, so this would be first equation. The second, it would be 22 g, so kind of 22 into 9.81 K times L0 minus, now the spring length is 100. So this is my second equation. So two equation, two unknown, we can solve it, right? Now let us take 2 by 1. It will be 11 L0 minus 100 on L0 minus 200. So this would be 11 L0 minus into 100 L0 minus 100. So 10 L0 equals to this would be 2100. So L0 will come out to be 210 mm. So with that itself we can say what would be our answer. Answer would be option B. So K is 1960. So let's confirm that also. Now substitute L0, value of L0 N1, we get 2 into 9.81 times K 210 minus 200. This comes around 19.62 divided by 10. This is 1.962 Newton per mm, right? So if I want to convert it into Newton per meter, I just need to multiply it with 1000 in the numerator, so it will be around Newton meter. So roughly, yeah. So roughly 1916 to Newton per meter, and that is close towards 1960. So now let's move on to the next question. Yeah. So this question is the deflection of a spring with 20 tons under a load of 1000 Newton is 10 mm. The spring is cut into two pieces, each of 10 tons, and placed parallel under the same load. The deflection of the new system is. Okay. Now we are given with earlier N1 is 20 tons, then load given is 1000 Newton. Deflection, earlier deflection is this. Spring is cut into two pieces, tons become 10 in each of the spring. We need to find the deflection where P2 P is the same. Okay. Yeah. So we know the load deflection, or let's say stiffness of the spring is given by GD464 RQN, right? Yeah. Now if I write K1 for like GD4 64 R cube times 20 as K1, so what would be my K2? That would be GD464 R cube into 10, and this would be equal to if I write here, there's 20 to 2 times of K1, right? Yeah. Now earlier with 20 tons it was the load kind of P delta now this should I use this the same okay. Now one more thing, K is equal to P by delta. Okay, so I can write it as P by delta 1, and this K2 is equal to P, no, now for second case, since it would be in parallel, K equivalent would be equal to K2 plus K2, that would be kind of 2K2, and this comes around 4K1, right? Yeah. Now this K equivalent would be equal to P by delta 2 with the same thing. Okay, let's use this 1 and 2. Let us take it step by step. 1, this is 2. So from K equivalent is equal to 4K1, this would be this. Yeah, from now K1 is equal to P by delta 1, so 4K1 is equal to P by delta 2. So 4K1 can be written as P by delta 1 equal to P by delta 2. P gets cancelled out. Delta 2 can be written as delta 1 by 4. Since delta 1 is 10 mm, delta 2 would be equal to 2.5 mm. Okay, so this is it. So in this question, the spring with 20 tons under the load of 1000 Newton gets deflected by 10 mm. Okay, the spring is cut into two pieces each of 10 tons and placed parallel under the same load. So the K equivalent would be equal to the 4 times of K1. Okay, where K1 is the stiffness what I was having the earlier spring. So our stiffness now becomes 4 times of it. The deflection corresponding to the same load will now become the it will be one fourth of the displacement what it was having earlier. So 10 by 4. 10 by 4 comes around 2.5 mm. So this is it. Next question. Two equal lengths of steel wires of same diameter are made into two springs S1, S2 of mean diameter 75 mm and 60 mm respectively. The stiffness ratio of S1 and S2 is, stiffness is given by GD4 64 RQ N. Now in this question, G is same, D is same, this would be same, this would be same, R is change. Okay, so can write it. So we are given with D1 is 75 mm and D2 is 60 mm. Okay. Consequently, can write it as R1 is 75 by 2, 60 by 2. Now S1, we can see that K is inversely proportional to RQ. The S1 by S2 would be equal to 1 R2 R1 Q, and this would be equal to R2 is 60 by 2 and this would be 70. So this is it, 60 upon 75 cube, right? Two equal lengths of steel wires of same diameter are made into two springs. Did I make any mistake? Okay, so this number of turns also plays a role, because the length of the wire, that will also come handy, right? The number of turns and how can we convert that into terms of radius of the spring? Okay, so number of turns, okay, just wait. This is 64 into n. Now number of turns, how that can be found? Length of the pitch, length of the wire, okay, so 2 pi r times n, this would be equal to length of the spring, right? This my length of the spring can be written as like this. Stiffness can be again written down as 64 RQ 2 pi r upon L, and this can be written as GD4 2 pi by 64 upon r square. Okay, so this will just erase this thing. Now in this case, this are same, this is also same, r changes, so this would give me k is inversely proportional to r square. Now so that can be also written as k is inversely proportional to d square. I can write now as s1 upon s2 is d2 upon d1 square, and d2 is 60, d1 is 75 mm. I can write it as 60 upon 75 mm square. So this is the answer. The answer would be option A, 60 upon 75 square. So this is a very good question. I actually forgot that number of turns would be different for the different the spring diameter, because the length is same for all. Moving on to the next question. A spring of stiffness 1000 Newton per meter is stretched initially by 10 centimeter from the undeformed position. Yeah. The work required to stretch it by another 10 centimeter is. Okay. A spring of 100 is stretched initially from the work required to stretch it by another 10 centimeter is. The question is, initially there is L0. From there it is stretched by L0 plus 10 centimeter, or L0 plus 10, so that is 0.1. This is in meter. Okay. Then again we want to stretch it by another 10 centimeter. That would give my final length as this, L0 plus 0.2 meter. Okay, so we want the work done from first to second. Okay, and that is so work done from for first case, it would be equal to half kx square, and that is equal to half L0 plus 0.1 minus L0 square. So W1 was this, half into 1000 into 0.1 square. This was 0.01 505. This is 5 joule. Now we L0 plus 0.2 minus L0 square. We want to find this. So this would be equal to half into K is 1000 into 0.2 square. So this would be 500 500 0.04 minus W1, that is 5. So this is 20 minus 5, this will come out to be 15 joule. Because in this I am taking from what? From the undefined position, but W2 is actually from the first defined part to the second one. So we are subtracting the work done from the undefined to the first part. Yeah, so answer will come out to be 15 joule. Thus consequently our answer would be option D, 15 joule. Moving on to the 16th question. That is the 6th question for this session. Okay, so the question is, a closely coiled helical spring of 20 cm mean diameter is having 25 coils of 2 cm diameter around. The modulus of rigidity of the material is 10 to the power 7 Newton per centimeter square. The stiffness of the spring is, so let us write what all is given. So mean diameter is given as 20 centimeter, that I can write it as so I can write the radius of the spring as 10 centimeter. Now number of coils is given as 25. Diameter of the wire is 2 centimeter. Modulus of rigidity of the material G is 10 to the power 7 Newton per centimeter square. The stiffness of the spring is, so we need to use this formula to calculate the stiffness of the spring, 64 RQN. I think everything is given, we just need to substitute the formula values. So this is 10 to the power 7, D is 2 to the power 4, 64 R 10 Q, N is 25. Okay, so 2 to the 4, 4 is 16, 400. This would be 10 to the power 3 into 10 to the power 2. This would be 10 to the power 2. Thus its answer would be 100 Newton per centimeter. Okay, the answer would be option B, 100 Newton per centimeter. Okay, now let's, okay, so I made a mistake here. This is not elasticity, this is modulus of rigidity. Okay, so now let's move on to the questions. Let's do this question first. In a closed coil spring, the other quantity is remaining same. If the wire diameter is tripled, then the stiffness of the spring compared to original one will become. Okay, so first thing first, stiffness formula is given this. Okay, wire diameter is tripled. In the given question, this is what it is given. Here everything is kept same, that is K is directly proportional to 4 to the power D to the power of 4. Thus my stiffness K2 by K1 can be written as D2 by D1 to the power 4. This can be simplified further. It is K2 will come out to be 81 times K1. Thus my answer is option B, 81 times. Okay. Yeah. Moving to further questions. Question is, in an open coiled helical spring of 15 coils, the stresses due to bending and torsion are 80 megapascal and 100 megapascal respectively when the spring is loaded axially. The mean diameter of the coil is 5 times the wire diameter. Find the maximum allowable axial load for a maximum extension of 20 mm. Consider E is 210 GPa, G is 80 GPa. So let us write it as let us write all the things which are given. Number of coils is 15. Stresses due to bending sigma B is 80 megapascal. Due to torsion, we can write sigma T as or else say tau 100 megapascal. The mean diameter of the coil D no is 5 times of D. Find the maximum allowable for maximum extension. The maximum extension delta max is 20 mm. Other things given are E is 210 GPa, that is 210 into 10 power 3 GPa, and this is 80 gigapascal. That can also be written as 80 into 10 power 3 megapascals. Okay. Now let us write it down. We need to calculate maximum allowable axial load for maximum extension of 20 mm. Okay. So we need to calculate the load, maximum load, right? So we know with the flexural formula, it is given as sigma B by I, right? I by Y, and this would be in the context of spring if the axial angle is given. So it is equal to PR sine alpha, where R is D by 2. So this would be equal to 2.5 D. Okay. Now in this sigma B is what? 80. I would be pi by 4, sorry, pi D 4 by 64. I would be equal to D by 2, and this is P. R is 2.5 D sine alpha. Yes, further simplifying, 80 pi D cube 32 2.5 PD sine alpha So again we can write it as P sin alpha equals to, so if I can write as 2.5 down here, 80 into pi into divide by 32 divide by 2.5. So this comes around 3.14 d square. Okay. Now similarly with the torsion formula Nt, and that is equated with this PR cos alpha, so that would give me P cos alpha equal to 7.85 d square with the torsion formula. Now with this 2 I can write alpha, we can find alpha, tan alpha, or 1 by 2 Vk tan alpha equal to 3.14 upon 7.85. This is 0.4. So if I take tan inverse of 0.4, this comes around 21.8 degree. Now now we have P sin 21.8 as 3.14 d square. I can write it as P is sin 21.8 into 3.14, so this is 8.45 d square. Now from the maximum deflection, that is delta max, this is equal to 64 PRQ n upon G T4 cos alpha, this is cos square alpha upon G plus 2 sin square alpha upon E. This is 20, I think, yeah, 64. P is 8.45 d square, R is 2.5 d, Q n is 15 d to the power 4 cos 21.8 degree cos square 21.8 degree upon G is 18 to 10 power 3 plus 2 sine square 20 is 210 into 10 power 3, right? Yeah, 210 into 10 power 3. So let's solve this. Okay. So 64 into 8.8. Sorry, this is 8.45, right? Yeah. So 64 into 8.45 into 2.5 cube into 15 divided by cos 21.8 into cos, okay, cos 21.8 divided by t plus 2 into sine 21.8 1.65. So 3 5, so d comes around 1.65 by d. So solving this, it comes around d value as 12.12. Now I can write p as 8.45 d square, that is 8.45 12.12 square, and this comes around 1241.25, roughly 1241 Newton. Thus you can write answer would be option B, 1241 Newton, 1241 Newton. Okay, yeah. Moving on to the next case, next problem. Question is, a closed coil helical spring is to carry a load of 600 Newton. Its mean coil diameter is to be 10 times that of the wire diameter. The mean coil diameter of the spring, if maximum shear stress in the material of the spring not to exceed 150 Newton per meter square. And the options are 10.09 mm, option B is 13.82 mm, option C is 11.28 mm, option D is 15.2 mm. So let us write It is to carry a load of 600 Newton. Mean coil diameter is 10 times that of the wire diameter. We need to find the mean coil diameter of the spring. Mean coil diameter of the spring if maximum shear stress this will not to exceed the, okay. Now this tau max, it's given using the uh, torsion formula. So it is given uh, so torsion formula. With the help of torsion formula, I can write is this the torsion value. This would be equal to P into T by 2. P element of inertia is pi d 4 by 32, the d by 2. So this will be equal to 16 to the 4 8 P T pi d cube. T is 10d, right? So that is 80 P on pi d square. Let us okay. So here we are given with 150, 150, 150, and I can write 80 into P is 600 pi d square. I can write d square as 80 into 600 pi into 150. So 80 into 600 divided by 150 divided by 101.859. D is so taking root of this, this comes around 10.09 mm. This my mean diameter would be 100.9 mm, right? So, with the given question, actually the question is asking one's mean coil diameter, but it should be here wire diameter. Then my answer would be option A, 10.09 mm. Otherwise it should be multiplied with 10 times and it should be kind of 100.9 mm. Then that would mean coil diameter, right? Yeah, Okay, moving on to the next question. A helical spring is fabricated by wire 20 mm in diameter around cylinder having 200 mm diameter. Compute the number of turns required to permit an elongation of 100 mm without exceeding a shearing stress of 130 megapascal. Modulus of rigidity is given as 82 gigapascal. So let us write first what is given. So wire diameter is 20 mm. Cylinder diameter is given as 200 mm, so that would be a kind of the radius of the diameter of the coil. We need to find the number of turns required to permit an elongation of 100 mm. Shearing stress as 130 megapascal. G is given as 82 gigapascal, so that can be written as 80 into 10 power 3 megapascal. Yeah. Yeah, so this is the question. Now let us so this is here, right? To calculate tau max, we use a correction factor times 8 PD upon pi dq, right? And this Ks can be written as 1 plus d upon 2d. So this is equal to, so I can write it down, this so this would be equal to 1 plus d is 20 to 200, so 1 point, this would be around 1.05. Now let's substitute all the values here. 130, 1.05, 8, P is not given, right? D is 200 pi d cube. So with this we can calculate P. So P would be equal to 130 into pi into 20 cube divided by 1.05 divided by 8 divided by 200. So this comes around 1944.79 Newton. Yeah. Okay. Now the deflection, this is equal to 60 so let me see this. The deflection would be equal to what? 64 PR cube N upon GD4. That is equal to, if I write it in terms of d by 2, so this will be 8 PR cube N GD4. Let us substitute everything. 100, this is entering 100. 8 P is 1944.79. R is, sorry, here is D cube, 200 cube, and G is 82 into 10 power 3, D4 is 20 to the power 4. So this will get N as 100 into 20 to the power 4. This comes around 10.54. So roughly we can say it's equal to 11. The correct answer is option D, 11. Yeah. Moving on to the next question. So in this question primarily two formulae has been used, this and this. Yeah. And to calculate this, you use this. Rest of everything is given, you just need to substitute the formula. Next question. A closed coil spring has a stiffness of 1.5 Newton per mm under 70 Newton maximum load and 130 Newton per mm square maximum shear stress. The solid length of the spring when the coils are touching is 45 mm. Find the mean diameter of the coil and number of coils required. Modulus of rigidity is given as 42 gigapascal. Consider stress concentration factor K equal to 1. So earlier which we used K as here the value is given as 1. Okay, so it's a lengthy question. So we are given with stiffness value as 1.5 Newton per mm under P equal to 70 Newton and torque max 130 Newton per mm square. The solid length of the spring when the coils are touching, so kind of N times D, because when it will touch this would be equal to 45 mm. Find the mean diameter of the coil and number of coils required. Given modulus of rigidity as 42 to 10 power 3 megapascal, K equal to 1. Okay. So first thing first, using the formula for the spring, and that is given as this 64 GD to the power 4 GD to the power 4 64 R cube, and that can be again simplified as 8 GD4 64 D by 2 8 R cube or D cube. D cube N, let us substitute 1.5 G is 42 into 10 power 3 d to the power 4, 8 d cube n. So again it can be simplified. N can be written as 45 by d, right? Let it be as of now. So write d4 as 1.5 times 8 120 d cube n upon 4200, right? This is just one. Now with the case of maximum shear stress, oh man, so that would be equal to 16 phi d d by 2 by pi d cube. Okay, now this can be written as tau max is given as 130 so 16 into p value is 70, so d by d pi d cube. So t can be written as 130 into pi into 2 divided by 16 divided by 70. 0.729 dq. Now this is 2 and this is 3. Okay, so let us substitute everything in 1. So substitute d and n in terms of d in 1. Thus this would be d to the power 4 120 into d cube is 0.729 d cube to the power cube. N is 45 by d divided by 4200. This would be equal to d4 120.729 cube, and this would be 3 3 9 8 45 4200. Finally d to the power 4 will come out to be 42 divided by 120 divided by 0.729 cube. 55. This comes around 20.0758. Imply T equal to 2.116 mm. Thus my D would be equal to 0.729 2.116 cube. 6.9. Let me do the correction. Check it. 130 into pi divided by 16 divided by 70 into 2. So if I take this kind of 0.72 172 d cube so this will come around 120 into 172 comes around 28.94. Where am I making a mistake? 120 into 0.72 cube, right? Into 45 divided by 420. So this is where I am making a mistake. So this is 12, not 120. 1.58 12. Right. So I substitute it here. 12. So this is where I was making a mistake. Let's see. 12 into 0.72 Q into 45 divided by 42. So now it comes around to 8.38. This will come around 3.79 mm. 3.79 Q. So consequently it will come 39.98. So it is roughly around there. Okay, because of the round of error and all. Okay. Okay, so if I take this as 7 to 10, then it comes around 4, 8. Okay, it was a lengthy question, a bit calculative, I would say. Let's do the next question. Question is, a closed coiled helical spring is made of steel wire of 6 mm diameter, has 10 tons of mean diameter of 65 mm, and the pitch of the coil when the spring is unloaded is 15 mm. Determine the axial load when applied gradually will cause the coils just to close up. Okay, kind of it will touch altogether, right? And G is equal to 80 gigapascal. So, so deflection, total deflection would be when it gets closed up, right? Total deflection would be 10 times uh, the pitch minus the diameter. So this would be 10. Pitch is 15. This is D. Oh, this is given as 6. Yeah. So this is 90 mm. This is the total deflection, right? Now we know the deflection formula is GD4 64 R cube N, or GD4 8 D cube N. Oh, sorry, this is for the stiffness. Okay, I get confused quite some time. No, this formula would be this, because K times delta, so P R Q N G D4. So this is the formula. Okay, we need to find the axial load. P would be equal to GD4 64 R cube N. P by delta, and this would be delta. Yeah, let's substitute. J is given as 80, this is 80 into 10 power 3. D is 6 to the power 4, delta is given as 90, 64 r cube, 65 by 2 cube, number of turns is given as 10. Let's calculate this. That's all, it will give the answer. So 80 into 10 power 3, 6 to the power 4 divided by 64 divided by 80 to 10 power 3 into 6 to the power 4 into 90 divided by 64 divided by 10 divided by 65 by 2 55 this comes around 424.72 Newton. The answer would be option C, 424.7 Newton. So in this everything is given, only thing to think about is this total deflection thing. So in the total deflection it says the coils just close up, so all the coils will start touching. So from unloaded length to the when the coils are touching, that would be my total deflection. So pitch minus the diameter of the coil, that is my expanded length, like the gap thing that gets removed, right, when the coils touch. So that times number of turns, so that is my total deflection. Okay, moving on to the next question. So this coming question is a bit lengthy one, so you guys need to check it out properly. So the question is, an open-coiled helical spring has a mean radius of 200 mm, 18 coils of wire 20 mm diameter at a pitch of 100 mm. Find out the maximum normal and shear stress in the wire when the spring is subjected to an axial load of 150 Newton. So first thing first, let us write what it is given. So mean radius is given as 200 mm. Number of coils is 18. Diameter of the wire is 20 mm. Pitch is 100 mm. And my axial load is 150 Newton. So this is all what is given. We need to find out the maximum normal stress and maximum shear stress, okay, according to the given condition. So first let us find the helical angle. So that is equal to P on 2 pi r, and this would be equal to 100 to pi r raised to 100. This alpha would be equal to 4.549, or write it as 4.55 degree. Now further twisting moment, mt, that is given by P cos alpha, right, and that is equal to P is 150 r is 200 cos 4.55. So this is equal to 4.55. This is equal to 29905.45 Newton mm. Similarly, we can find the bending moment mv equal to p r sin alpha, that is 150 into 200 into sin 4.5455. This would be equal to sin 155. So this is equal to 2379.87 Newton mm. Now this is what it has given. Now so tensile force, axial tensile force in the wire, if I write it as T, it would be equal to P sin alpha. This would be equal to 200 into sin 4.55, sorry, 150 into a sin. So this is equal to 11.89 Newton. Okay. Next, transverse shear force V, that would be equal to P cos alpha, and this would be 150 into cos 4.55, 150, 149.52 Newton. These are all. Now let us work out the stresses. So first, axial stresses. Axial stress. Axial stress due to tensile force sigma T. I'll write it as, so this would be equal to T by A, and that is 11, that is T pi by 4 D square. So this would be equal to 11.89 into pi by 4 D is 20, I think. Yeah. So let us calculate this. 4 into so this is 0.0378 Newton per mm square, or I'll write it as megapascal. First, so this is a normal stress, right? Now shear stress due to twisting moment, sigma tau, oh sorry, rather read as tau, due to T, capital T. So this would be equal to 16 T 8 pi d cube. Let us substitute. This is 299.145 pi d cube. Let us calculate this. 16 into 299.0545 divided by pi divided by, this is 19.038 megapascal. So now shear stress due to shear or direct shear or this transfer shear force. So we can write it as tau V, and that would be equal to 4 by 3 VA. So 4 by 3 V is 149.52, A is 5 by 4 D square, that is 20 square. So this would be equal to 49.52 divided by 3 divided by pi and divided by d. So this comes around 0.634 megapascal. So okay, anything else left? Okay, so we are left with one more thing, normal stress due to bending moment MB. So that is sigma B, and that would be equal to 32 MB by d cube. 32 into B is 2379.87, 2379.87 by d cube. Thirty-two into 2379.87. This is 3.03 megapascal. So this now total normal stress sigma n, or I'll just write sigma equal to sigma t plus sigma b, and sigma t is 0.0378, 3.03, so this would be 3.0678 megapascal. Total shear stress tau would be equal to tau T plus tau V. This would be equal to 19.038 plus 0.634. 19.038 plus 0.64 20. So this is 19.672 megapascal. Now the final thing, maximum shear stress. Tau max would be equal to what? Sigma by 2 whole square plus tau square. So this is 3.0678 by 2 whole square plus 19.672 square root. This is equal to 3.0678 by 2 square plus 19.672 square. This is equal to 387.219. So this comes around 19.68 megapascal. In continuation, maximum normal stress sigma max would be equal to sigma 2 plus sigma by 2 whole square plus tau square, and this would be equal to sigma by 2 plus tau max. This would be equal to 3.0678 by 2 plus 19.68, and finally it comes around 21.21 megapascal. Yeah, so normal stress is 21.21 and shear stress 19.68. So 21.21 and 19.68, it's roughly closer towards shear value is 19.68 and 21.21. Yeah. So our answer is closer towards option C. So please go through this carefully. In this question, we need to find the normal stress and shear stress due to bending, twisting, then the axial tensile force acting on the wire itself and the transverse shear force acting on the wire itself, and then we calculate the shear stresses. Then to find the maximum shear and normal stress, we use the formula as provided earlier in the previous discussion sessions. So sigma by 2 whole square plus tau square, we take this root, we get the maximum shear stress and maximum normal stress is sigma by 2 plus minus root sigma by 2 whole square plus tau square. Okay, please go through this carefully. This is a very good question, I'd say. Okay, so in the above question, this is in continuation with the above question. So for the problem in question number 7, find out the deflection due to the given loading condition, and this time we are given with the value of Young's modulus and modulus of rigidity. So for this, it's a direct calculation based formula, where the formula to be used is 64 p r cube n upon cos alpha d to the power 4. This would be cos square alpha upon g plus 2 sin square alpha upon e. Yeah, okay, so let us substitute whatever has been provided earlier. 64 p was given as 150, I think. Yeah, 150 Newton. Yes, 150. R was 200 cube. Number of turns 18 upon cos, we calculated it was 4.55 degree. Then d square d to the power 4 is 20. Then cos square 4.55 degree upon g is 42 into 10 power 3 plus sin square 4.55 210 into 10 power 3. Let me cross check the angle again. 4.5, yeah. Let's calculate this. Into 64 into 150 into 200 cube into 18 divided by 20 to the power 4 and divided by cos 4.55. So this comes around 205.53 to 205.325. So roughly option C. Yeah, let's move on to the next question. Question number 9. A vehicle weighing 60 kilonewton is moving at 3 km per hour. Find the number of springs required in a buffer stop to absorb the kinetic energy of the vehicle during a compression of 200 mm. Each spring has 20 coil diameter of 250 mm. Diameter of the spring rod is 20 mm and the modulus of rigidity is 42 megapascal. So C. Vehicle weight I can write as 60 kilonewton, that is 60 into 10 power 3 Newton. Velocity is 3 kilometer per hour, that is 10 power 3 upon 3600. This would be 0.83 meter per second. Okay, next, number of coils in a spring is 20. Coil diameter is 250 mm. Diameter of the spring rod is 20 mm. Modulus of rigidity is 42 into 10 power 3 megapascal. And the compression, it's given as 200 mm. Okay, the kinetic energy stored in the vehicle just write it as KE half mv square, and that would be equal to W by G square, half into 60 into 0.81. E square is 0.83 square. So this is around 2106.72 joules. Further, let P be the load in one spring. The compression in it is given by 64 PRQN upon GD4. Yeah, and energy stored by one spring E is equal to half P delta. So this would be equal to 32 P square RQ and GD to the power 4. Okay, don't okay, rather I'll just convert this. So half P delta P can be written as GD4 delta upon 64 R cube N. That is GD4 delta square 128 R cube N. Let's calculate this. G is G is 42. D is 20. Yeah. Delta is 200 or 100. Yeah, 200. Square 128. R is 250 by 2 cube, and number of turns in a coil is 20. So let us calculate this. So 42 into 10 power 3 into 20 to the power 4 into 200 square divided by 128 divided by 20 divided by 250 125 cube. So this comes around 53 53 760 into 10 power minus 3 joule. That is, E comes around 53.76 joules. I would say this is millijoule. Newton mm. Yeah, so number of springs required equal to kinetic. This would be equal to 2106.72 upon 53.76. 2106.72 divided by 53.76, and this comes around 39.1875. Roughly we can say it's 40. Yes. Okay, so 40 or 39. Just say 39. The answer would be option D, 39. Okay. Now moving on to the last question of today's session, and this will wrap up the today's session as well as yeah. So let's do this. So the question is, two closely coiled helical springs A and B are similar in all respects except the number of turns. Number of turns in A are triple of the number of turns in B. What is the ratio of deflection in spring A to B? Okay, so first thing, we just need to know the formula for the deflection, and that is equal to 64 p r cube n upon g t to the power 4. Yeah. Now it's being said that every aspect is same, only number of turns are different, right? And you can see from here that deflection is directly proportional to the number of turns. That would give us delta A upon delta B is equal to NA upon NB, and it's given, okay, first thing first, it's given that NA is equal to 3 times of NB. Okay, so 3 NB upon NB, that is 3. So delta A and delta B equal to 3. The answer would be option B, 3. Okay, rest of the questions has already been solved earlier. Yeah, that is okay. So this concludes our today's session. I hope it's clear for you all. If you guys have any doubt, you guys can use the discussion forum and post your doubts. I'll try to resolve your doubts as much as possible. Okay, so best of luck for the course and the exam. And okay, see you guys. Take care. Have a nice day. Bye.